Hello, everybody. Welcome to the Science Cafe. Tonight, they don't let me say that yet. They give me a script, like they think I will read it. Okay, so I'm Sarah Wyatt, for those of you that don't know. I'm a faculty member in plant biology, and I'm also the vice president of Sigma Xi, the Science Honorary Society. Before we get started tonight, the next cafe, next week we'll have a cafe conversation, and that's going to be Stan Ellis at the School of Visual Communication, talking about photography and politics. So that should be pretty interesting. And then in 2 weeks, we have Dr. Ann Lokes, who is from she's from Biological Sciences, and she's going to be talking about health issues in female athletes. But tonight, we have Nancy Sandler from Physics, and don't forget, if you ask questions, interact in some way or another. We have t-shirts to give away. There are a limited number, so you need to get involved quickly if you want a t-shirt. I encourage you all to enjoy, have a good time, and please, it's all yours.
Let me see how this works. Okay. So hi, it's really a pleasure to be here. This is my first time here, so you will forgive me for my inexperience and stop me if you don't understand me. As you can hear, I am not American. I have a heavy accent, and I am used to be stopped for questions because people don't understand my accent. So please feel free to interrupt me anytime. So I am a theoretical physicist. I do theory. I don't work in a lab. I collected a couple of toys to bring and show today, but this is not my expertise. This is not, to play with toys directly is not my expertise. My expertise is to think and to imagine. I like to say that my job is extremely creative. I am not an artist, as you may understand artist, but I am kind of doing that sort of job because what I try to do, no, okay, like this, okay. So what I try to do in my office with my books and my computer is to imagine what happens inside things that make them the way they are. So my creativity is a little bit constrained by reality. I have to explain this or this, right? But otherwise, I am completely free to imagine anything. And the other constraint that I have is that whatever I imagine, the workings, the internal workings that I am thinking go on to make this material the way it is, I have to check if my model predicts something that can be observed. And that's when I go and knock on the door of my experimental colleagues and I knock on the door of my experimental colleagues and I try to convince them to set up an experiment to check if what my imagined model predicts can be observed. So that's basically summarizes my job. So I like to say that I am sitting in my office like this all the time, basically, which is not so far from the truth. So today I wanted to tell you about a new group of materials that are very, very exciting, both for their potential applications in devices to make our lives easier and better, but also because they allow us to investigate very fundamental questions about nature. And I put the title From Lasagna to Pancakes just to set in your mind an image of what we are going to describe. We are going to describe materials that look either like lasagnas or like pancakes, okay? So, before doing that, oh, great. There. before doing that, I need to remind you some basic ideas about how do we classify matter, the matter that we see around us. So I hope that you remember that we have this very broad classification, and we said there are things that are solid, like water in the ice form. There are things that are liquid, like water in the fluid form. And there are things like are in the gas phase, which are like the clouds, okay? And each one of them have their own characteristics. Solids are hard, we can touch, they have a given volume. Liquids are not hard, they flow, they move around a lot, they occupy the volume where they are contained, and gases are completely all over the place, okay? When I started, I said that I am a theoretical physicist, and going a little bit deeper into that definition, I am a condensed matter physicist, because I studied matter that is either in the solid or in the fluid form, okay? I don't deal too much with the gas form. So, part of the interesting question about condensed matter is that it has a very wide array of properties. So it can be transparent, it can be soft, with this type of softness, elastic, or this type of softness. It can be bouncy, can be hard, can be shiny, okay? Can attract other things, okay? And all these properties, all these different properties, stem basically from their elementary constituents. Now, I hope that you remember also that the elementary constituents are the atoms. And I hope you remember what an atom is. For starters, you cannot trust on them, as that the well-known folklore says. So this is our standard picture of an atom. An atom is the smallest unit of matter that we can think of that is made out of positive charges that move around and that we call electrons, and negative charges that I call electrons, and positive charges that are in a very reduced region that is called the nuclei, that we picture it at the center. So the electrons that are near the center, we call them core electrons. They are closer. They are very hard to separate from the center, while electrons that move outside are more mobile. They are relatively easy to get outside. Now, with this point as a starting point, with this unit as a starting point, all the things that you see here and all of the things that you see around you are made of atoms. And atoms give each material, each element, its unique properties. Now, one way that atoms give these properties or provide these properties is by the way that they are arranged in space. So you can ask, if I have one atom and I take it as a stamp and I start repeating it continuously, okay, I will create what we call a solid material. A solid material is nothing else than a periodic array of atoms. Now, you can ask, how many different arrays can I get in one dimension? Well, in one dimension, I can have one type of array only because I have a line, and they will differ by the separation between the two atoms or the atoms that I put there in that line. Now, you can ask, how many arrays can I have in 2 dimensions? So if I have an atom and I want to move it or to stamp it in 2 independent directions, how many different arrays can I end up forming? And when you calculate and you go through this exercise, you find out that there are only 5 types of lattices that you can create, 5 types of these regular arrays. And you can keep asking, saying, okay, how do the atoms, this is a 3-dimensional object, right? It occupies a volume in space. So how do the atoms array in 3 dimensions? And when you do the same exercise in 3 dimensions, you discover that for one atom, you have 14 different ways of putting them in order to fill the whole space, or the whole space that you are interested in. So if I have 2 atoms that are different, let's say I can play the same game. And at each point here, I can put 2 atoms. And you see that the freedom that you have to put these two atoms at each point is enormous. You can have 3 atoms at each point. And because of this complexity, because of this freedom that we have in ordering the atoms and putting different number of atoms at each point site, we have the whole variety that we see in properties for solid materials. Now, let me check my notes that I am okay. So, I said that atoms give, according to their arrangement, their placement in space, give many of the properties that characterize solid materials. Now, how do they give these properties? Well, I say, well, if I order them in a particular way, I will determine certain set of properties. Now, what else characterizes the properties? And what characterizes many of the properties is the freedom in which the electrons can move around once the atoms are ordered in this fashion. So we have materials in which electrons can flow very, very easily, and these materials is what we call normally conductors. These are metals. This is a metal. In these materials, the electrons of each atom can move from atom to atom very easily. They flow. You can imagine like a flow of water. Well, electrons are pretty much like a flow here. There are a lot of them, and they can move very easily if I push them. Now, there is the other extreme in which electrons cannot move at all. So these are materials that are extremely bad for electricity. Cork is one of them. In these materials that we call insulators, electrons stay fixed with each atom. They don't go from atom to atom. They don't like to jump so much. Now, you may wonder, is there anything in between these two? Well, what characterizes a conductor? Well, it's good for electricity, so if I want to send a signal, I would definitely use a conductor. The problem with a conductor is I cannot stop that signal once it is sent because the electrons are moving continuously. They are usually bright, they get hot very easily, they are easy to manipulate mechanically. You can take a metal and you can bend it, okay? So they have a lot of good properties. Insulators, on the other hand, tend to be hard, tend to be useless for electricity if I want to send signals, opaque. They are not very good transmitting or keeping the heat. So there, for sure, must be materials between these two. One more thing that I want to add is that in conductors, in metals, the idea that electrons can move easily, we have our own jargon in physics to describe that. We say that you have a lot of electrons and you do a little bit of push and they go and move around. There is no gap. There is no minimum amount of energy that you need to give the electrons for them to start moving in a conductor. In an insulator, it's the opposite. In order to get the electrons moving, you have to give a tremendous push to them. Sometimes the push is so big that you melt the material, you destroy the material in your attempt to make the electrons move around. So we said that the insulators have a large gap. There is a large energy gap that we have to go against in order to make the electrons mobile. Now, for sure there must be materials in between these two. And of course, nature is rich enough that gives us material between these two, and these materials are known as semiconductors. Semiconductors, the most common semiconductor that you know is silicon, and is the basis of all our electronics these days. This is an example of a semiconductor made out of silicon. Silicon oxide is what you find in the beach, in the sand, okay? This is a sample of a hard disk, something that is inside your computer, and they are made out of silicon. We know how to grow these materials very well, with a high degree of precision. In fact, in this same campus, I have a colleague of mine who has a big toy machine that is called molecular beam epitaxy, in which he grows particular semiconductor materials. So the most famous semiconductors is silicon, but there are others that are not famous, not so popular, but they are extremely, extremely well known for us in basic research because they are extraordinary materials to study. These are gallium arsenide, the nitrides that have applications in lasers, in general, semiconductors are very good for optical applications, for heat applications, and for electronics. Why? Because what characterizes a semiconductor is that they have a gap like an insulator, so electrons there to move, they need a push, but they don't need such a huge push like in an insulating material. And on the other hand, you have a lot of electrons moving like in a metal. So they combine both characteristics. If I want electron moving, I need to do the right amount of push to them, and I will keep them moving. If I don't want to get them moving, I just don't give that push, okay? So I can control the current of electrons to that material. Now, once we characterize all these materials, you start asking, well, is all there is? Is there something else? And of course, there are other materials with other properties. And the first that come to mind, and that is the focus of this talk, are what we call semi-metals. And graphite is one of them. Graphite is what you have here in your pencil, inside your pencil lead. It's a material that's extremely common in nature everywhere around the world and has been used for a long, long time. So when I started working on this topic in particular, I became very curious about the history of the material, and I found out this book that is interestingly written by an engineer who likes to write about the history of everyday objects, and he tells us the story of the pencil in particular. And the story of the pencil starts, of course, with the story of graphite. There, just to make a long story short, he tells that by the 1600s, the elements that humans used to write were parchment, very expensive paper of the day, and ink. And the problem with ink is that you cannot erase ink. So if you made a mistake in your document, you were toast. You needed to change your parchment paper, go and kill another sheep and get and clean all the stuff that you need to get the paper and start all over again. So it was a big deal to have something in which we could make notes or we could mark that was erasable. So as it happens, it seems that a family of shepherds were taking their sheep in England to eat, and in one of their wanderings, they ended up in a cave type of place where they saw this dark piece of pebble, of rock. And they started playing with the rock, and they noticed that the rock was able to make marks. And most remarkable, that these marks could be erased. So they say, great, we can use this to mark all our sheep, and we can nap all day, and we don't have to worry about where they are around because we can find them if they mix with other sheep from other places. And then when we have to return it, we can clean up these marks because they are erasable, and the wool wouldn't be affected, and nobody will be mad at us. They hit the discovery of the century. Because as you can imagine, when people realized that you could use graphite as a marker, poof, business was exploding everywhere. Very fast, we discovered how to pulverize it, how to extract it, first of all, how to recognize it, how to extract it, and how to pulverize it and to encase it in little wooden sticks so we could use it more individually. And that's how we ended up with the pencil. And something that I found extremely interesting in this book, and that I like to quote every talk that I give, everywhere, is this, that the first pencil that was made here in the States was made by the woman. And there are not many women in science, not in hard science, not in my field, so I find beautiful that this gentleman decided to start that paragraph with the sentence, in the beginning there was a woman. I feel honored by that. This was a young lady who was a teacher and who learned how to pulverize the graphite and how to mix it with glue and pigments to give it color and how to put it in a wooden case, that is to make the first pencil. It's interesting that this reference I found in many other places after I found it in this book, and nowhere there is a record of the name of the woman. Interestingly enough, one of the persons who benefited a lot with the invention of the pencil was Thoreau. If someone can repeat that name in case you didn't, the poet Thoreau, whose family was the owner of one of the first one of the first factories for pencils in the States, the Ticonderoga pencil. And he could enjoy that wealth and be a poet and pursue creative activities because he was well off. But her name doesn't appear anywhere. So, okay, so I digress with that story. I am passionate about it. So, what is graphite made of? Graphite is made of carbon, and this is a picture of the carbon atom. The carbon atom has a nuclei, as I said, with positive charges, and has 6 electrons, 2 of which are very, very close, to the nuclei, and 4 of them that can roam around. So when we put many atoms of carbon together, these 4 electrons like to jump from place to place. And depending on how we order the carbon atoms in these lattice structures that I mentioned, that's the property that we get. We can put them in pyramid structures, and we get diamond. We can put them in layer structures, pretty much like this, and we get graphite. In graphite, the carbon atoms are forming planes that are weakly coupled to each other, weakly bound to each other. In each plane, they form hexagonal shapes. And the strength of this attachment between the atoms in the plane is very strong. So it's very difficult to separate the atoms that are in the same layer. But it's relatively easy to separate them, those that are in different layers. So when you learn that, you say, perhaps we can separate them. And we have been trying to separate them for several decades. Many people growing graphite with methods like the molecular beam epitaxy that I mentioned before, they were able to grow it, but they were not able to separate one layer from the one underneath. And they know that separated it because they saw it sliding. Graphite is a very good lubricant because the layers slide on top of each other. Can we separate them on a more regular basis? And you will be surprised to know that, of course, you do it every day. You separate the layers every single time that you write. Because when you write with a pencil on a piece of paper, if you take a look closer to what you leave on the paper, you will see that you leave these little speckles, these little freckles, that if you have the right instrument, which in this case is known as the scanning electron microscope, what you see are layers like this that look like silk, all folded, all crippled on top of the surface. Each of these layers is a graphene layer. It's one single atom. So I want you to realize that with this, we are able to work with materials with a thickness that is like if you take one hair strand in your head, if you have average hair width, and you take one hair lengthwise and you cut it 100,000 times. That's the thickness of this thing. It's really, really tiny. And we are doing it every day. Now, graphene, this monolayer, this single layer, has its own name and is known as graphene. And it keeps many of the properties of graphite. For example, when I said that graphite is a semi-metal, what I meant was that electrons in graphite move. There are not many electrons to move, as in a normal metal, as in a conductor, but there are enough that you can detect. And they don't need much of a push to start moving. So it's not like in an insulator. We say that it doesn't have a gap. So you apply a little push and the electrons move. You don't have as many, but you have. So it's, again, something intermediate between a conductor and a semiconductor. So I brought a little demo to show how do we know that graphite is a conductor. I have a ball here that has a little light inside. if current goes through it, so if I plug a battery to it, the light will shine, right? Well, the battery is inside here, inside. There is a light bulb with a battery inside, but it's not plugged, so that's why it's not shining. If I complete a circuit, if I give a path for the current to move around, the circuit will be closed and the light bulb will shine. So I will make a circuit with a pencil and, with a pencil and a piece of paper to show that the pencil is producing a wire as good as this one that I have here. And I will ask for you to be patient with me because, as I said, I am not an experimentalist. So, let's see if I can plug these wires here. Come on. Come on. Yeah, I am much better sitting in my chair thinking, as I said. I am not. There you go. So I am connecting it. You see? There. This is very delicate. Very delicate. Come on. Okay, it's taking too long. I don't want to. So that's what it's supposed to do when the circuit is closed. These are very well done, as you can see. Okay, let's see if that, okay. So, my circuit now is open because it's not connected again. And what I am going to do is, I'm going to leave it there. I will take a piece of paper. I will take my pencil, and I will draw a line. And I will draw a line thick enough, you see? I feel like a magician every time that I do this. So let's see. I claim that this is a conductor. This is a wire. Let's see if it works. Thank you, everybody. So, these little freckles that we see on the screen are conducting. We can use them as wires. Imagine what we can build with wires so thin and so tiny. The discovery was so remarkable that led to the people who was able to isolate them to the Nobel Prize in 2010. So these two gentlemen, and the Nobel Committee said that the Nobel Prize was awarded for groundbreaking experiments regarding the two-dimensional material graphene. And when you read that, you are really impressed because it's, wow, these guys really made it, right? They must have used very elaborate equipment, expensive techniques. They must have been like, pfft. Now, no, you will be wrong, because what they did was something pretty simple. They said if you can separate the layers of graphene every time that you write, it must be pretty easy to separate them. So why don't we scratch pencil lead on top of a Scotch tape? Glue the Scotch tape, separate it, and repeat this procedure many times. Eventually, you are bound to find one flake. So they use a lot of time, a lot of student hours, as we call them, to do this. There were a lot of students breaking Scotch tapes on and on all the time. And then they were scratching the rest, and they were putting it on a microscope. And they were amazingly lucky that the substrate where they deposited the graphene was such that they could see it with the naked eye. If they had chosen a completely different substrate, I don't think that they would have detected it. But they were lucky. It was just by chance. In this physics department, in this physics laboratory, they did this on a Friday night. They hold these Friday night sessions that they call creative session. This is at the University of Manchester in England. And what they do on Friday is like a free-for-all. They come up with the craziest ideas and the craziest methods with beer and chips, and they chat, and that's their diversion on Friday nights. And that's when they did this, on a Friday night. So this is how we imagine graphene, as a single sheet that is softly, smoothly ripple, okay? Because it's extremely thin, it's extremely sensitive to whatever interactions you have. And this is why my talk goes from lasagna to pancakes. So we were able to separate layers that are weakly attached to each other, and we can deal with each of them separately. So you can imagine that after this discovery, the first question that everybody asks is, well, can we use this? What can we use this for? And many groups, because the material is cheap, it's easier to find out, and it's easier to obtain in a relatively clean, usable form. The research on graphene has exploded all over the world, all over the world. So there are a lot of countries, the European Union puts a lot of money on research on graphene because the potential applications that are expected from the material are humongous. And I just chose two examples. One, I took the slide for a business side. So companies are seeing possibilities as graphene, to use graphene as a purifier of water, as in chemical separation, in material for packaging, in sensors, in batteries. These are all proposals for real devices, for real applications, in which real companies are now investing money to it. But companies are not the only ones that are taking advantage of research in graphene, universities too. And this is a slide for a university in Japan, where they show the applications that they can have if they oxidize graphene, if they do graphene oxide. And they can use it as an additive for polymers, they can use it as electrodes. Nokia has a prototype for a telephone screen, for a phone screen, that is very flexible and very resistant, because one of the main properties of graphene is that it's very hard. It's a very hard material to deform under certain circumstances. So you can see that this is kind of basic research for which institutions are benefiting all around the world, and also companies are taking advantage of it. I just wanted to mention what my research is on this material. I started working on understanding the properties of this material 10 years ago already, and I started looking at what happens if you wanted to cut graphene, even smaller, if you wanted to do ribbons with it, let's say thinking about wires. These days, I am interested in the properties that come up when you strain graphene, when you deform it. It has been shown that graphene is so hard, so resistant, that you can pick up an elephant with it without the membrane breaking. So at the research level, the way that we study strain is, for instance, depositing graphene on substrates that are prepared in a particular form. For example, we can deposit certain molecules in a very controlled manner, establishing, let's say, periodic arrays, and then we deposit graphene on top, and we create the modulations that we want. So I want to ask, what are the properties of this graphene that has this particular modulation? Does it have something that we can use or that can be interesting? We can do it even at a more delicate, at a more individual level. We can take an atom or a bunch of atoms and deposit it on a substrate and put graphene on top, like in this image. These are little mountains that are graphene on silicon dioxide, and the mountains are made out of platinum atoms that were deposited there. And they are deposited with a particular toy machine that is called the scanning tunneling microscope. And in our physics department, we have two colleagues who have this instrument and can do this. Okay? They can arrange atoms one by one on a surface at room and at very low temperatures. And I can measure what happens there. So, for instance, the latest research that I was involved in was, okay, what are the properties of this isolated mountain? So just to give you an example, I figured, well, an isolated mountain like that is like a bump. Let's imagine that has a Gaussian type of shape, a bell type of shape. And with that assumption, I calculate where do the electrons lie, where do they like to be. And what you find is that they like to be in very particular spots. They don't like to be roaming around. When the mountain is formed, they like to stick around. And they like to stick around forming a specific pattern. And our papers have the name flower all over them because they look like flowers, 6-petal flowers. So, is that all? No, that's not all. Because graphite is not the only material that has this lasagna structure. We have come back to study all the materials that we know under this new light and realize that there are a lot of materials that share this structure. They go under the name of van der Waals materials because the attraction between the layers is a particular force that is known as van der Waals force. So we have now a whole zoo of materials that we can mechanically exfoliate, as they fancily call the name in which graphene is insulated. And we have this is an example. And what we are doing these days is not only to isolate them, but to combine them and build lasagnas with them again. So this is, for instance, a feature of one of the most respected journals in advanced materials and was dedicated last year to these different two-dimensional materials that go beyond graphene. So we are entering into the stage where we are beyond graphene and exploring all the other materials. So what is the physics or the new devices that we can get from these new materials? Where there are very promising prototypes of devices that are investigating these days. This is one of them, where we can create photovoltaic applications mixing structures of graphene and one particular material that is known as molybdenum disulfide, that's the name. There are proposals to build transistors. There are transistors. Transistors are the things that you have, the circuits that are in your computer. These are transistors, okay, that are printed here, extremely, extremely thin. So we can get that with mixing these materials. There is the idea of using, and this is extremely important as a research field in many universities, to use graphene oxide as a purifier of water. So it's a research area that is being developed in many places, as you can imagine, because water is our most essential resource, and this will provide a cheap and easy way to clean it. This has been already proven that you can use graphene oxide to clean radioactive messes. You just have a liquid where radioactive material lays down, and you throw a little bit of graphene oxide, and the radioactive material clumps, and it's very easy to extract and clean it up. There are batteries that are flexible in the way. Again, as I said, Nokia is playing with the iPhone's cover. Samsung is playing with making these batteries. And not long ago, piezoelectric materials that when you bend or stretch, they develop electric fields. They separate charges. You can have electric signals out of them. Yes, have been developed this year, earlier this year. Yes, question.
What is it structurally about graphene that makes radioactive material attractive?
It's graphene oxide.
Oh, the graphene.
It's graphene oxidized. Oh, yeah, the question was, thank you. The question was, what makes graphene especially attractive to radioactive materials? Well, I said that it's not graphene per se, it's graphene with oxygen, and that's at a level of chemistry that I don't feel completely prepared to answer properly. But if you deposit oxygen randomly on graphene, it has to be a real oxide, cannot be in an ordered structure, then the chemical reaction for certain radioactive materials occurs and it grabs it. So chemists in the audience perhaps could provide more information. Yeah? So I was saying that this one was just made up this year, and something that I wanted to point out is that, again, in our own physics department, we have one professor who is able to grow this material. In fact, we are studying this material nowadays. And this professor, which is also a colleague of mine, is characterizing this material optically. So he's trying to understand the optical properties of the material to see what use we can get out of it. Now, this has to do with applications and devices. I am interested in that, but I am much more interested in the physics, fundamental questions that these materials bring up. And I just listed some of them, the ones that immediately pop in my mind. For instance, can we make a magnet? A very, very thin magnet. Can we make a magnet that has the orientation that we want or changes the orientation in any way we want? Can we see fundamental physics? Now, by fundamental physics, I refer to the physics that is usually associated with these large accelerators, like the one in Chicago, Fermilab, or the one in Switzerland, where from time to time we read in the newspapers or hear the God particle has been discovered, or the Higgs bosons and stuff like that. So things that made up everything beyond the atomic scale. Now, there are a lot of weird particles and weird phenomena occurring at those energy and length scales that these days can be observed in these materials. And one of the latest one involves a particle called Majorana particle, named after an Italian physicist, and that has been predicted to occur inside the nuclei of the atom. That has to be, in order to be found, has to be smashed with enormous energy so it can be broken and we can see it. Well, evidence of Majorana particles have been found in some of these materials, and the question is, wow, can we do this type of experiments at a more regular scale? Another question is, how do they dissipate heat? Heat is dissipated by the motion of the atoms around their positions. Now, they cannot move much. How do they move? How do they dissipate? Are they good heat conductors? Can we have a magnet with moving electrons? Normally, magnets are materials in which electrons don't like to move very much. They are not very good conductors in general. Can we make up one of those? Can we see how the electrons turn out to be there? How do electrons move when the light shine on them in these materials? If I change the laser, if I shine with a laser, how does the movement depends on the laser frequency, the laser color? Or if it's not a laser, it's just a regular lamp, how do they behave? This is the topic of one of my students' thesis, for example. Can electrons develop superconductivity? No. The amount of money that you pay in your electricity bill is because when we send the current, the electrons bounce back. They are what we say backscatter. They resist the motion. So what you pay in your bill is the resistance of the electrons to move through the wires from the place where they are created to your own device, to my computer, okay? Now, we have been looking for materials in which this resistance decreases or goes down enormously. And this is what we call superconductors. The bad news is that the superconductors that we find work as such at very, very low temperatures. So they are not practical. We keep looking for them, and these two-dimensional materials surely are promising. So I just want to conclude with these fundamental questions, and I am open for questions. Yes? Mm-hmm.
They were doing some studies on the graphene,
Mm-hmm.
and they were producing a fabric from
Mm-hmm.
graphene.
Mm-hmm.
And they were showing it's not 100% transparent, but
Mm-hmm.
mostly clear.
Mm-hmm.
And it was like under the sunlight, it was
Mm-hmm.
reflecting the other side,
Mm-hmm.
make it invisible.
Mm-hmm.
How is that possible?
How's that possible? So the question is, how can graphene be transparent and at the same time invisible? No, kind of that's, well, yeah. Okay. Uh-huh. Mm-hmm. So let me see if I can wing my way. we see, because the light that hits upon us gets reflected and gets to our eyes. That's how we see. So in order to see a material, the material has to bounce the light back. Otherwise, we will not see it. So any material that is transparent, it's because most of the light, okay, goes through it and doesn't return to our eyes. Now, graphene and depends on how graphene is made and how many electrons are available in graphene. Graphene happens to be invisible at what we call the optical range, because the light that goes through it goes directly. You can think that I like to think sometimes of light as little particles, the things that we call photons, that come, hit the electrons in graphene, the electrons capture all the energy, and they start moving like crazy. So there is no photon to come back to my eye. Okay? So in that sense, graphene is good for optical properties that absorb energy. Okay? The fact that it's elastic is what makes it elastic in certain deformations, not like this, but like this. Okay? And that's what makes it useful for clothes. Now, the same property, let me see if I can tie. The fact that can absorb light so easily, insert in the frequency range where we see, makes it also a good candidate for heat trapping. So that's why people think of graphene as a material to incorporate in clothes. The idea is that it will trap the heat from the body, it will not let it out, so and it will accommodate to your body temperature. I will have to go way more technical to go beyond this explanation. I don't know if I answer. Yes?
On a completely different note.
Uh-huh.
So the original experiment involved Scotch tape. I'm guessing since then they figured out a different way.
Oh, yeah.
What process is used?
Oh, there are many. This still is one of the favorites. This, yes, that's a Scotch tape. It's still one of the favorites by many groups that don't require a high flakes, large flakes, and very high purity, because it has, this method may have a lot of defects. Now, methods to create graphene. There is this molecular beam epitaxy that I mentioned before that basically consists of a machine that has nozzles from which the atoms are expelled one by one, and they accommodate on a substrate. So in that way, graphite is grown. The atoms, imagine little balls rolling around, and they accommodate one on top of the other in kind of a disordered way. And under the right shooting conditions of this pressure and temperature, you can stop this growth, and you can separate the last layer. This is the molecular beam epitaxy method. There are a lot of chemical methods by which graphene, by chemical reactions with solvents and all that. One of our colleagues in engineering, she is doing catalysis of coal, and in one of the cathodes, she found out that she has graphene. Very bad quality, but graphene. So silicon, in silicon carbide, it's also, you evaporate the silicon atoms, and the carbon atoms that remain accommodate in such a way that the upper layers don't bond. So they are loose with respect to one another, and then with proper techniques you can come and separate them. One technique is to deposit some polymer that you glue it, you separate, and then you dilute the polymer in a solvent, and you have your layer. So there are other techniques using carbon nanotubes, in which carbon nanotubes are is graphene roll in a cylinder, and again, with chemical substances, they can unzip the nanotube, and they open up. So yes.
How expensive is graphene to mass produce?
I have no idea. How expensive is graphene to mass produce? Well, I guess I have no idea. I have no idea about the costs. You can ask my husband, I am very bad with money, so it's like, it's not a consideration even. But what I can tell you is that a lot of people who work in the laboratories were doing research on graphene, they finished their studies and they created their own companies and they are selling graphene online. So if you do Google, there is one company, Graphania, that some of my colleagues used to buy samples, and you can check the prices. I imagine that it will depend a lot for what you wanted, because that will give you the degree of purity and orientation and all that. Yes. She. Okay.
Earlier you said that businesses are trying to use graphene to purify water.
Mm-hmm.
So how does that work?
So, again, it's kind of the question is how can graphene be used to purify water? Is this thing? So basically, what is chemistry involved is the way that molecules. Graphene is transparent to water, if you want, but it lets the water molecules go through it, but doesn't attach to them. But it does attach to impurities that are in the water. And again, chemistry is like the detailed account of how that happens goes beyond my basic physics. Yes, sorry.
So you talked about like the strength of like each individual layer of graphene, like the bonds in between them are really strong. But like, so when you have a pencil, you layer them on. But even if you wouldn't that make a pencil only useful in one spatial dimension, like in this dimension up and down? But how can you like get
Yes.
a pencil to
Because
write
that's a good question. So the question is, if graphite is layer, and the layers can separate between them, but not in the other directions, a pencil should be useful if the layers in graphene are in this orientation only. Because if they happen to be in a different orientation, I wouldn't separate them. I wouldn't be able to write, right? So what is inside here is it's polycrystalline. So you have little crystals in all directions possible. So it's not a unified, it's not something like this that we call a pure crystal, which the order is perfect. You have to imagine that there you have mixtures in all directions. So depending on your direction of writing, you will be displaced in this layer, or you may be displaced in this layer, or you may be displaced in this layer. Yeah? Yes? Mm-hmm. Yes, yes. Yes. Mm-hmm. Wow. The question is if there is a way that I can explain why the interlayer bond is so strong while the intralayer bond is so weak. Well, I will hide again behind the chemistry question, the chemistry answer. The idea is that these electrons that are in the carbon atom, when they are together with electrons from another carbon atom, they mix in very specific ways. These specific ways are, we say that they hybridize in a very specific way. For this particular compound, they hybridize, forming what are known as, these bonds are called sigma bonds, that it's a mixture of two types of electrons that have different characteristics, let's say, okay? Although all electrons are identical, they are not exactly identical. Some of them we can label differently, and we can identify them. So the mixture of these two electrons in this particular way creates this bond. This is what is called a covalent bond. These electrons are shared, if you want, equally by the two carbon atoms. The remaining electron, that is the one that wasn't shared here, that wasn't hybridized here, is the one that is shared between the atoms in the layers. And this is more like what is known as a metallic type of bond. It's van der Waals. It's not purely metallic. It's a bond that decays very fast with the distance. So as soon as you separate these two if something gets between the two of them, it's like they are isolated very easily. So the nature of the mixing between the electrons and how they are shared between two neighboring atoms is what gives the difference between here and there. That's why in diamond, for instance, it's the same atoms, but in diamond, when the atoms are together, the electrons mix in a different way. And that's what makes diamond diamond. It's a completely different material than this. So at the end of the day, everything reduces, if you want, at how the electrons are shared and how they are combined, if that answers. Okay.
Any other questions?
Is there a specific commonality that's seen between the different, like, graphene and graphene-like substances that makes them so different than other molecular substances that enables them to have this ability to separate into layers?
Well, what I think, and okay, if there is any feature common to graphene and all the other two-dimensional materials that makes graphene special, I think that well, there is the main, I would say, the main feature is that carbon is a very common material. It's very easily to find everywhere. We are made out of carbon. So it's ubiquitous, I think that's the word. It's everywhere. Now, from the point of view of the physicists, graphene has, electrons in graphene have a remarkable property. They behave inside, they move inside as if they didn't have any inertia, any opposition to motion, which in all the other materials that we have found until now, that's not the case. In all those other materials, electrons they resist a little bit of motion. They have a gap. These other materials are gap materials. You need to push the electrons to move. In graphene, it's not. And not only they behave as with no inertia, with no resistance to motion, they move easily. That's why it's a semi-metal. They move at a constant velocity, at a constant speed, with a value for the speed that is 1/300th time the speed of light. So the connections between the two, well, I find that remarkable. But as far as I know, those are only found in graphene and in this carbon material, not in the other ones. The other have other properties which are interesting, but not these ones. And the fact that it's cheap and it's it's very accessible to everybody. So graphene is being researched all over the world. So one of the quotes by one of the Nobel Prize winners was that what he really liked about this discovery, because he was famous before within the physics community, but what he liked was that he was able to show that you can do extraordinary science with your everyday means. You don't need to have fancy equipment or be in a very prestigious or expensive university or institute. If you are curious and you let your curiosity drive you, then you are bound to make discoveries, and I like that.
Sure. One last one.
Are all of these layered substance all carbon-based then? Is that a requirement? Or
No.
is it the family,
It's
like carbon, silica, are you going down?
part of the game is going down in the periodic table. Part of the game is to discover. We have many different techniques to identify the crystalline structure, how the atoms are ordered in a particular material, and so we can identify very easily which materials are layered. And then the question is, what will be the best technique to separate one layer from the other? So.
What is the unifying characteristic of substances that are layered? They're not all carbon.
No, they are not all. In fact, I was going to show this one. This material is molybdenum disulfide. It's molybdenum and sulfur, and they are mixed together. The atoms happen to be arranged in an hexagonal pattern in the layer. But instead of being identical like in graphene, which are both carbon, here is molybdenum and sulfide. In fact, there are 2 layers of sulfide and 1 layer of molybdenum in the middle. It's more like a 3-layer kind of thing for this case. There is another one that is boron nitride, which is boron and nitride, and they are literally in the same layer. So no, it's not carbon. Part of it is the geometrical, the lattice that they form when they arrange, and the lattice depends on how they share their electrons, basically. So we are trying to guess beforehand which combinations of materials will have this property. And some people are doing the guessing, and some people are being more practical and say, okay, let's try with this one, and let's go back to that one. There is phosphorus, for example. The phosphorus come in very different versions. There is one in particular that is known as black phosphorus. That one has this property too, and it seems to be the next graphene for the basic research. So, yeah.
Okay, on that note, we're going to end. I'm sure Nancy would be happy to talk to any of you and answer any more questions you have. Could we give her one more round of applause, please? Thank you very much.
Thank you very much.
Next week, don't forget, we have a cafe conversation. Stan Ollist will be talking about photography and news or politics. And then in 2 weeks, we have another science cafe with Ann Laux talking about, from Biological Sciences, talking about women's health issues with athletics and sports. Thank you very much. I appreciate your attendance.